Then you need a massive input data file. And I tend to use very simple name embedding an infix here. I use the _G. This is run G. I have notes elsewhere that says, what is this? This is actually the base case, the best simulation of the conditions in that canopy. There are some control settings up here, but let me jump to a few things down here. Line 6, we have the longitude, latitude, and the central meridian of the time zone. That's needed to get the proper calculation of solar angles. Line 7 is the name of the weather data file, and line 8 says that it begins on July 1st. This is needed because you may want a simulation that only takes a segment of this, say, July 4th to 20th. But the program has to know how many days to skip over to get there. It has to know that the file begins with July 1st, for example. This set of variables on line 9 determines how many individual locations within the canopy are simulated. The light penetration to every one of these points is computed, and then also using the different angular orientations of the leaves, it figures out the illumination and energy balance on the leaves. It sums up all these different contributions to give a final whole canopy flux, or whole crown flux. So the values 555 mean that I sample 5 separate radii from the center of the crown. N theta equals 5 means that I sample 5 different zenith angles, and then N phi means 5 different azimuthal angles around the canopy. Next line, 10. I pre equals 1 means that the light penetration arrays have already been calculated in a previous run and saved. Because if you change a physiological parameter or whatever, it's not going to change the light interception. And these light penetration arrays take some time to calculate. So it can save time to have them saved from a previous run, which puts them in a file that's specified in line 11. So you retrieve that light penetration file. Okay, here we get into some interesting things. I'll come back to these other lines. Let's look at leaf photosynthetic capacity and so on line 14. Okay, this 100 says that the maximum photosynthetic capacity in the leaf is 100, and that's in units of micromoles per square meter per second, same as photosynthesis rate. 0.8 is the curvature parameter in the response of photosynthesis to light level. 0.8 means it's pretty close to a Blackman curve, but it's almost a universal value among most C3 plants. The next two parameters are to estimate the dark respiration, which has to be debited from the gross photosynthesis. The 0.1 says that on average the dark respiration of leaves is 10% of their maximum photosynthetic rate. We have found this in our research on trees, and other people have found 8 to 10%. The 30 says that at a deviation from any temperature other than 30, we apply the standard Q10 of 2, the exponential scaling of respiration. Okay, and this is more plain physiology on line 15. I use the Ball-Berry model for stomatal control. It has a, well, you can look up how it's structured. It has a slope, which in this simulation is set to 10, which is almost a universal value again for C3 plants. Jump over here, it has an intercept of 0.02. That's basically the minimum stomatal conductance after everything else is shut down. The 0.5 says that I subtract the dark respiration in composing the photosynthesis rate. used in the Ball-Berry index, and I'll explain in other documents what other values could be used. The 1.0 for this parameter HBBD says that the excuse me, stomatal response to humidity is in proportion to the first power of the relative humidity at the leaf surface. That's the standard formulation of the Ball-Berry model. I did some simulations with a power of 0.5, so it's much less sensitive to humidity, trying to see if I can simulate what happens on days of strong advection. It's not relevant for knowing how the model actually runs. Tolerance here says to stop the iterations of the calculation of stomatal conductance when it converges to 0.0001 moles per square meter per second in standard molar units that are used now. The stomatal model has to be iterated along with everything else, because the photosynthetic rate, the stomatal conductance, the leaf temperature are all nonlinear equations involving each other, and I have a novel way of iterating the solution that always converges, but this is determining when we stop. Let's jump back to this parameter here. This is the surface relative humidity to use in the initial simulation of the dark of photosynthesis in order to get the dark respiration rate that's going to be then fixed throughout the whole simulation. I say use 0.5 for surface relative humidity. It's a good average value. The minus sign, perhaps Ali says, use the actual Ball-Berry response. Do not use a model which is not responsive to humidity in calculating this photosynthetic rate. Let me go back here now to some leaf optical properties on line 13. This says that the absorbance of the leaf for photosynthetically active radiation, PAR, is 85%, very standard value for normal green leaves. Only 5% is transmitted through the leaf. The remaining 10% is diffusely reflected. Similarly, in the near infrared, 35% is absorbed, 0.217, 21.7% is transmitted. The soil has a reflectance of 30% in both the PAR and NIR. All of these values are used primarily to calculate the secondarily scattered light from leaves that then reaches other leaves and helps drive photosynthesis and transpiration. Right, now the next set of parameters here are for the stress response of stomatal conductance to water stress. Okay, it's best probably to look inside the code and some other documents, figure out what these all mean. In the current simulation, they're rather irrelevant. I'm simulating an unstressed canopy. Some more environmental information. We have to know the CO2 partial pressure in the free air. It's 34.5 pascals, corresponding to a mixing ratio of 385 parts per million and a total air pressure of 88,500 pascals. Air pressure is needed for various conductances, aerodynamic conductances. The 0.05 here is representing the crosswise dimension of the leaf, 5 centimeters, irrelevant to creating the boundary layer conductance for heat and so on, and water vapor. This is an unusual parameter here. EPS move. It is the modification of the thermal emissivity of the sky from the standard values computed from temperature and humidity. In our arid area, the sky temperature is typically about 40 degrees Celsius below air temperature. A lot of other models fail to use this. They overestimate the downwelling radiation by 100 or more watts per square meter. I can simulate the effect of overlooking that by setting FF's move to something. If I set it to 1, it uses a hot sky that radiates at the same temperature as the air, basically. The next line here, obviously, which you could pronounce as change value, is a holdover from the times when I would run this model iteratively. After I got this far, I could say, oh, wait, I want to go back and change the value of one of these parameters. It's irrelevant now. The next parameter here on line 19 is the foliage density in square meters per cubic meter. Use the value 0.65 after analyzing some of the shadows at the Tornillo orchard. There were no structural measurements. This is very close to the 0.7 value that we actually measured in the Salopec orchard here in Las Cruces. This parameter rho over C1 on line 20 is a parameterization of the canopy aerodynamic conductance to the ambient air. It's a value that was used in the classic canopy models of peers, sellers, and co-workers. And that can be explained in another document. The next lines are very extensive. Simulate 81 different trees. From a central tree, I go 4 columns and 4 rows in each direction, adding other trees that will possibly get in the way of light interception at various locations in the central tree. First entry here, lines 22 through 24, describes that central tree. It's given coordinates as the origin, 0 and x, 0 and y, and the z direction indicates the height of the center of the crown above the ground, so it's 5 meters up. The 8.5 values represent the major and minor axis of the crown, represented as or an ellipsoid of revolution. The program allows this to be very general. If I set these equal, it's a sphere. So then other things like the angles of inclination, zenith and azimuth of the central axis of the ellipsoid don't matter. Set them to 0. The next lines, the next 240 lines, give the coordinates and orientations of the remaining 80 trees.